I'm introducing the next speaker, Mr. Ian Glacken. He is a very experienced geologist, and he is an executive consultant today at Snowden Optiro, based here in Perth. He also served as director for both Snowden and Optiro. At Snowden Optiro, Ian's been focusing on training, resource reviews, and audits, and specializes in reconciliation training and studies. Ian has carried out reconciliation reviews in Ghana, South Africa, Zambia, West Australia, and South Australia in the past few years, and has also been contributing quite heavily on the GeoReg 2024 reconciliation changes as part of the working group. Welcome, Ian.
Thank you very much, Bruno. So this is a presentation which was essentially put together by Richard Haigh. Richard Haigh is a senior geologist at Vale, formerly based in Indonesia, but now based in Brisbane. And as it turns out, Richard couldn't be here because he's in Jakarta this week. So I'm going to present his slides together with some of mine. And it's appropriate because at Optiro and later at Snowden Optiro, we worked with Vale or STM for about 4 or 5 years now. So we're sort of presenting some of our work and some of Richard's work. STM stands for Sumbawa Timor Mining. So here is a very exciting disclaimer for Vale, STM. Got that? So where are we? Well, we're in Sumbawa. Sumbawa, you can see on the map there, it's just to the east of an island that lots of Australians know, which is called Bali. Those of you that aren't from Australia may not have heard of it. I understand that Sumbawa is good for surfing, good for mountaineering, and also, as you can see there, it's good for volcanoes, as is most of Indonesia. So we're talking about a deposit called Onto. Onto is a porphyry copper, and it's going to be an underground deposit, a block cave deposit, and you can see there it's quite close to the coast in southern Sumbawa. Haven't been to Sumbawa yet, unfortunately. So this is what it looks like. What we're looking at there is a envelope, and that envelope is defined by a 0.2% copper copper grade. So we're talking about copper and gold here. As we'll see, it's quite a bit of gold in there as well, but it's essentially a copper ore body, a porphyry copper. And what you can see is the drilling, and you can see the drilling has gone down to a certain depth, but from that deep hole you can see that there is certainly extensions, which may be a third lift of the block cave at some point. So geologically, it's a hybrid porphyry copper, high sulfidation. We've got a number of intermingling porphyry stocks. Essentially, once you get below the sort of upper levels, it's chalcopyrite rich. So that's the main mineralizing element. You've got advanced argillic alteration, and then you've got a number of the classic sort of porphyry copper assemblages. And the Onto team have recognized 4 essential alteration assemblies which correspond to the domains in the resource estimation. It's very young, less than a million years old, and the main mineralizing event about 40,000 years ago. So very, very young. And you can see there the geological interpretation in the top slide, and in the bottom slide you can see the alteration assemblages. So this is how Vale intends to mine it. They've got this volume, and that green outline defines the lift 1 and lift 2. So 2 lifts, block cave, and beneath that there's an exploration target. In terms of the actual resource estimate, it's a moderately sized ore body, 3 billion, which is not the biggest, it's not the smallest by any stretch of the imagination. The grades are quite reasonable, and you can see there, once you sort of look at all of the contained metal, there's quite a bit of gold in there as well, over 37 million ounces, and quite a bit of copper. So it's quite a big target for Vale, for PTSTM. And one of the issues is the drilling. The drilling is quite expensive. It's very mountainous, as you can see, and they need to optimize the drilling. So the challenge for Vale was actually defining the drilling density for indicated and measured. there was some ideas based on some sort of drill hole studies like Oscar was mentioning to you in the previous presentation. And the Vale global group required a little bit more proof of concept with respect to that. And so there was a benchmarking study of underground copper porphyries, and they showed that the drilling densities were much more tight than what Vale was proposing. So a benchmarking exercise was prompted by that study, and this is what we're going to talk about. So you've heard the 9015 thing mentioned a couple of times already. Oscar mentioned it in the previous presentation. It's based on work by Harry Parker and Christina Dom. Apparently Harry was developing it in the 90s, but the paper, or one of the papers that mentions it, is the 2014 paper. And the essence is that as I mentioned to you quite a few times in these talks, we're looking at three things. We're looking at the overall confidence interval in grade. We're looking at the error in terms of the mean of simulations, and we're looking at different volumes. So for a inferred resource, we're looking at the entire resource, which in this case is very large. For an indicated resource, we're looking at annual production increments. And for a measured resource, we're looking at a quarterly production increment. And essentially that picture on the top right there sort of tells the story. What we're essentially looking for is that if we take the mean of the simulated data plus or minus 15%, if that is outside the 90% confidence interval for the range of simulations for those three block sizes, then it passes. That's essentially it. Now, Oscar would be very remiss if I didn't mention to you that that is just the starting point of the classification. The competent person needs to then consider things like data quality, assay quality, and so on. In this case, it's a big deposit, going to be mined by block cave, but you know, this is the starting point. So this is what we're looking at. So got a few slides. Oscar's presented these before, but I'll just go through them quite quickly. So essentially what we're talking about here is capturing geological uncertainty. So those of you that went to the MRE conference earlier this year would have noticed that modelling geological uncertainty was one of the main themes. And there's a number of ways of doing it. In this slide, we're looking at a couple of approaches. Plurigaussian simulation, which is really best for a stratified ore body where we know the sequence of the layers, and there's various versions of that, truncated Plurigaussian, and so on. What we're using in this case is something different, a sequential indicator simulation. It's a simpler approach, but one of the key points is that the domains don't have a sequence, and that's very appropriate for this ore body because there's no stratigraphic sequence for the domains. The domains are quite, I won't say chaotic, but they all in contact with each other. So in this particular case, sequential indicator simulation was quite appropriate. And here's a picture of the ore body, the block model, showing the four domains, which are essentially alteration assemblages, and that bar chart down the bottom shows the global proportions of those domains. And one thing that sequential indicator simulation will do for you is to preserve those global proportions with a little bit of uncertainty, ergodicity. So in the theme of this conference, interoperability, we use Studio RM for sort of patching everything together. We calculated the sequential indicator simulations in Asatis Neo and the grade simulations in Supervisor. And essentially we used the resource block model, which was 45 by 45 by 15. And the grade simulations were generated at a smaller block scale and reblocked up to the MRE. So we're using the connections between the three bits of software. And basically we had a whole series of realizations of the geological uncertainty, so sequential indicator simulations, and then within each of those we generated a number of grade realizations. One of the things I noticed at the conference that was a few months ago in Perth was that the CCG group, Clayton Deutsch's group, was saying that for each geological uncertainty simulation you only needed to do one grade simulation. We can discuss that, but in this case we actually generated a lot of simulations of grade for each simulation of geological uncertainty. So there's quite a few realizations in there. How many realizations? Well, in this case, we calculated for each domain 40 realizations of the geology, of the alteration zones, of the domains, and then with each one of those 40 there was 30 grade realizations. So that's quite a few realizations, as you can see, and it took quite a while, a lot of crunch time. So here's a picture, two pictures. The first picture is of the proportion of domain 1. Remember, 4 domains, and you can see there the variability in that proportion, and the overall average there is the green line. So that's there 40 realizations of the geological uncertainty. On the right, within one of those realizations, we've got 30 realizations of the grade uncertainty. So what you can see there on the right is the tonnage grade curve for the copper grade and the copper metal, copper tons and the copper grade. Not a whole lot of uncertainty in the grade. In this case, it's probably the case that the geological uncertainty was more dominant than the grade uncertainty, which you would expect for a sort of fairly disseminated porphyry copper gold deposit. So one of the things that we did, and David Barry mentioned this briefly this morning in his artist, we used some software to reduce the number of realizations using the simulation reduction tool, which basically takes 40 or 50 or however many you've got, and it gives you a smaller number. In this case, I think we chose 15, and it basically captures the same degree of variability as the larger number. So that was quite useful for reducing the amount of work that was done. Validation. You can validate the simulations by checking the proportions of the 4 domains in the simulation against the global proportions. Obviously, you can see that where we have a particular drill hole with a particular domain code, that is validated as well. And here's a picture showing on the middle screen there, the middle picture, that is the global proportions of each of the 4 domains. So that's the picture with the yellow thresholds on. The one on the bottom right is the reproduction of that in one of the 40 realizations. So you can see that the global proportions of the 4 domains were reproduced quite well. And then what you can see in the top right is one of the grade realizations, or a suite of the grade realizations showing the relationship between the drill holes and the raw data and the simulated data. Sorry. So you can see that the normal sort of simulation validation tools were used. So this slide shows the work that was done subsequent to that, and essentially we were given 3 data sets. The first data set, DS1 on the left, is the actual data set that supported that resource declaration that you've seen, and there's not a whole lot of drill holes there, 43 drill holes. Second one in the middle, DS2, is the additional drilling that was carried out. So they're actual holes. So you can see they doubled the number of drill holes and doubled the total meterage. The third one, DS3, actually shows the planned drilling, and what we're doing here is intersecting the planned drilling with the block model and retrieving the grade. So it's, if you like, it's simulated grades. So the essence of this study is to show whether that third drilling program, DS3, is sufficient to give us the upgrade in the classification measured and indicator that we want. So we're going to look at those 3 data sets, DS1, 2 and 3. So what we're looking at here is this is the way that we would evaluate that 90-15 approach. So what you're seeing on that graph on the bottom left is the schedule, essentially, over a 45-year schedule. So that's lift 1 and lift 2, and you're looking at the one of the grade curves for each of those. Grades for each of those realizations. And so what you're looking at in the top right is a summary of that. And to put you in the picture there, the mean grade is the purple line. The plus or minus 15% around that is the dashed red line, and then the 90th percentile. So in other words, the difference between the P95 and the P05 simulation is the green and the blue lines. So what you can see for the first 10 years is that we're not making it. We're not achieving that 90-15 approach. In other words, the grade plus or minus 15% is less than the 95% confidence interval. So that's failing our test for the classification. So we obviously need to do some drilling. Now the question to be answered was the planned drilling sufficient to give us what we wanted in that respect? So from an inferred resource point of view, it's very straightforward. Essentially, the whole thing makes it as an inferred resource. We're dealing with very large production tonnages here. So for all of our 3 data sets, the 2 existing data sets and the simulated additional data, we're passing the definition for inferred resources. So no problems there. I mean, it's definitely at least an inferred resource. Okay, so this is a bit complicated, this one. So what we're looking at now is the 3 data sets I mentioned to you. DS1, which is the original data set. DS2 in the middle is the double data set that was used. And then DS3 is the data set plus the simulated drilling. In other words, as I mentioned to you, the drill holes that come from the block model, they're simulated grades. And you can see that, as I've shown there on the right, following the future drilling, that is going to be sufficient based on the width of the 95th percentile, the P90 confidence interval. It's going to be sufficient to classify our first 10 years, which were previously inferred only. It's going to be sufficient to classify those as indicated. Again, with the proviso that the competent person needs to judge all of the other issues associated with classification, such as geotechnical, grade control, grade quality, assay quality, and so on and so forth. So given those provisos, that additional drilling would be sufficient to classify our first 10 years as indicated. And then when it comes to measured, is that going to work? So in this case, we're now going from an annual production volume to a quarterly production volume. So again, you can see there, based on that right-hand picture, which again is the existing data plus the simulated infill drilling, you can see that the confidence interval is sufficient to be able to classify most of it as measured. Remember that they weren't intending to classify the whole thing as measured, but they would have liked to classify at least some of it as measured. So the result of that simulated infill drilling program was essentially showing that would have been sufficient to classify most of the resource as either measured or indicated. So the use of simulation gives us an amount of variability. As I mentioned to you, the grade variability was very small. The geological variability was very large. I think we did a reasonable job with the geological variability. That has supported objective classification based on the 90-15 method. We can also use selected realizations of grade and geology to calculate project economics, such as net present value or rate of return, and then so for the project economics can be looked at through a number of probabilistic approach. So the idea of planning the future drilling and then working out what the grades of those drill holes were based on either a simulation or a block model, in this case, was quite useful. So essentially what we're doing is simulating the input or the impact of future drilling and answering whether it was sufficient to give us that classification. Now, of course, we might drill those holes, or Vale might drill those holes, and they might be very different to what was assumed. And that's always a risk that you take with these things. I mean, it's predicting the value of future information. But given that from a grade point of view, copper or gold, it's quite low variability, there's probably a good chance that doing that additional drilling will give them, they haven't done it yet, will give them that level of certainty that they need. There's a picture of Richard and Ignace on the top left there in the Vale offices in Jakarta, and me and Ignace pointing at the location of the ore body. Thank you very much.